In the infinite darkness between stars, where light takes millennia to traverse the void, there exist objects so precise, so mathematically perfect in their rhythm that when astronomers first detected them in 1967, some scientists genuinely wondered if they had discovered evidence of extraterrestrial intelligence beacons, placed by civilizations far older than our own. Lighthouses built to guide travelers across the cosmic ocean, signals repeating with such exactitude that no natural phenomenon seemed capable of producing them. And for a brief, electric moment in human history, we thought we might not be alone. And even after we understood what pulsars truly are, the reality proved no less astonishing than the fantasy, because what we discovered were the corpses of massive stars, collapsed into spheres no larger than cities, yet containing more mass than our sun, spinning hundreds of times per second, while broadcasting electromagnetic beams across light years with accuracy that rivals atomic clocks. What are these impossible objects, and what secrets do they hold about the violent deaths of stars and the fundamental nature of matter itself? The story begins on November 28, 1967, at the Mullard Radio Astronomy Observatory in Cambridge, England, where graduate student Jocelyn Bell Burnell was analyzing chart paper from a radio telescope designed to study quasars. And among the chaotic scribbles representing cosmic radio noise, she noticed something peculiar, a regular pattern of pulses, appearing at precise intervals of 1.337 seconds. And this signal, which she initially dismissed as interference from Earth-based sources, kept appearing at the same point in the sky as the Earth rotated, and the regularity was so perfect, so artificial seeming, that the research team jokingly designated it LGM-1 for Little Green Men, and for weeks they grappled with the possibility that they had detected an alien beacon, and the implications were so profound that they kept the discovery secret while they searched for alternative explanations. What must it have felt like to be among the first humans to wonder if we had finally made contact with another intelligence? But as more of these signals were discovered at different points in the sky, each with its own precise rhythm, the extraterrestrial hypothesis became untenable. No civilization would build so many beacons, and the explanation that emerged was in some ways more extraordinary. These were neutron stars, objects predicted by theory but never observed, the remnants of supernova explosions, so dense that a teaspoon of their material would weigh 1 billion tons on Earth, and they were spinning at incredible speeds, and their powerful magnetic fields were channeling radiation into narrow beams that swept across space like lighthouse beams. And when those beams pointed toward Earth, our telescopes detected a pulse, and thus a new class of celestial object entered human awareness. And Jocelyn Bell's discovery would revolutionize our understanding of stellar death and extreme physics, though controversially, the Nobel Prize for this discovery went only to her male supervisor, a decision that remains contentious decades later. How does recognition and credit flow in science, and whose contributions get remembered? To understand pulsars, we must first understand the life cycle of massive stars, because pulsars are born in the most violent deaths the universe has to offer, and a star many times more massive than our sun burns through its nuclear fuel at a prodigious rate, fusing hydrogen into helium, then helium into carbon and oxygen, then into heavier and heavier elements in a desperate fight against gravitational collapse. And this process continues until the core becomes iron, and iron cannot release energy through fusion. And at that moment, the star's fate is sealed, because without the outward pressure of fusion to counteract gravity's inward pull, the core collapses catastrophically, and protons and electrons are crushed together to form neutrons. And in less than a second, a core the size of Earth compresses to a sphere perhaps 20 kilometers across, and the outer layers of the star rebound in a supernova explosion that can briefly outshine an entire galaxy. What unimaginable forces are at work when matter itself is restructured at the subatomic level in a fraction of a heartbeat? The neutron star left behind is an object that defies ordinary comprehension. Imagine the mass of our sun, which is 333,000 times more massive than Earth, compressed into a sphere the size of Manhattan. And the density is so extreme that atomic structure as we know it cannot exist. And instead, you have essentially one giant atomic nucleus. And the gravitational field is so intense that if you could somehow stand on the surface, which you couldn't, because you would be instantly crushed, and vaporized time itself would flow measurably slower than it does on Earth. And if you dropped an object from 1 meter above the surface, it would hit the ground at a significant fraction of the speed of light. And these are not theoretical speculations, but mathematical consequences of general relativity applied to objects of such extreme density. How do we conceptualize objects that exist at the boundary of what physics allows? But neutron stars don't just sit quietly in space. Many of them spin, and they spin fast. And the mechanism that creates this rotation is conservation of angular momentum. Just as a figure skater spins faster when pulling in their arms, a collapsing stellar core spins faster as it shrinks, and a star that might have rotated once per month before collapse can emerge as a neutron star rotating hundreds of times per second. And the fastest known pulsar, designated PSRJ 174824446 AD, spins 716 times every second, which means that a point on its equator is moving at roughly 1/4 the speed of light. And this is approaching the theoretical maximum rotation speed before the neutron star would tear itself apart. What does it mean for an object with more mass than the Sun to be spinning so fast that its surface approaches relativistic speeds? These spinning neutron stars possess magnetic fields of staggering intensity, up to 1 trillion times stronger than Earth as magnetic field. And these fields are not uniformly aligned with the rotation axis. And charged particles near the neutron star are accelerated along the magnetic field lines. And as they accelerate, they emit radiation. And this radiation is beamed outward from the magnetic poles. And because the magnetic poles don't align with the rotation axis, the beams sweep through space like a lighthouse. And if Earth happens to lie in the path of one of these beams, our telescopes detect a pulse of radiation, and the pulse repeats with each rotation. And the timing is so precise that the best pulsars keep time more accurately than atomic clocks on Earth. How can such violent, chaotic objects produce signals of such mathematical perfection? The discovery of pulsars opened a new window into extreme physics, because these objects exist in conditions that cannot be replicated in any laboratory on Earth, and they serve as natural experiments, testing the limits of what matter can endure. And one of the most fundamental questions they illuminate concerns the equation of state of nuclear matter. What happens when you compress matter beyond atomic density? When neutrons pack together more tightly than they exist even in atomic nuclei, and different theoretical models predict different internal structures for neutron stars, and by precisely measuring pulsar properties, their masses, radii, oscillations, and behavior, astronomers can test these theories against reality. And what we're relearning is rewriting textbooks about the fundamental forces that govern matter at its most compressed states. What does it mean when the universe provides laboratories we could never build ourselves? Inside a neutron star, the conditions progress from merely extreme at the surface to potentially exotic at the core, and the outer layer, perhaps a centimeter thick, consists of iron nuclei and electrons packed into a rigid crystalline structure that may be the strongest material in the universe, billions of times stronger than steel. And below this crust, the density increases, and atomic nuclei merge into a sea of neutrons with a scattering of protons and electrons, forming a neutron-rich fluid unlike anything else in nature. And deeper still, the pressure becomes so extreme that neutrons themselves may break down into their constituent quarks, creating what physicists call quark matter or strange matter. And some theories suggest that the very core might contain exotic particles that exist nowhere else in the universe. How many states of matter remain unknown to us, existing only in the hearts of collapsed stars? The precision of pulsar timing has enabled discoveries far beyond the pulsars themselves, because these celestial clocks are so reliable that tiny variations in their pulses reveal the presence of other objects. And this is how the first planets beyond our solar system were discovered. Not around a normal star, but orbiting a pulsar, detected by the subtle rhythmic variations in the pulsar's timing as the gravitational pull of orbiting. Planets caused the pulsar to wobble slightly. And this was announced in 1992, before the first exoplanet around a normal star was confirmed. And these pulsar planets are utterly inhospitable worlds, bathed in intense radiation, probably the remnants of a stellar companion that was shredded during the supernova or formed. From the debris afterward, what might exist on worlds orbiting the corpses of exploded stars? And what could we learn from these radiation-scorched systems? Pulsars also serve as probes of the space between them and Earth, because as the radio waves travel through the interstellar medium, the thin gas and plasma between stars, they interact with free electrons, and different frequencies of radio waves travel at slightly different speeds through this plasma, an effect called dispersion. And by measuring how much the pulsar signal is dispersed, astronomers can calculate how much material lies between the pulsar and Earth. And this has allowed us to map the distribution of matter throughout our galaxy, revealing structures and densities that would be impossible to measure any other way. How do we use precise measurements of distant objects to understand the invisible matter filling the space between? Some pulsars exist in binary systems orbiting another star or another collapsed object, and these systems provide natural laboratories for testing Einstein's general theory of relativity, because the strong gravitational fields and high velocities create conditions where relativistic effects become significant. And the most famous example is the Hulse-Taylor binary pulsar, discovered in 1974, where two neutron stars orbit each other every 8 hours. And as they orbit, they emit gravitational waves, ripples in space-time itself, and these waves carry away energy, causing the orbit to gradually shrink. And by precisely timing the pulsar over decades, astronomers measured this orbital decay and found it matched Einstein's predictions with extraordinary precision. And this was the first indirect evidence for gravitational waves, decades before their direct detection in 2015. What does it tell us when observations, spanning decades, confirm theoretical predictions to multiple decimal places? The lighthouse analogy for pulsars, while useful, is incomplete, because unlike human-built lighthouses that shine continuously with rotating lenses, pulsars may actually produce their beams in pulses. And the exact mechanism of this emission is still debated, and it likely involves complex interactions between the magnetic field, the neutron star's rotation, and the plasma surrounding the star. And different models propose different geometries and emission mechanisms. And despite decades of study, we still don't fully understand the details of how the beam is generated and modulated. How comfortable are we with using objects we've observed for 50 years, but still don't completely understand? The population of known pulsars has grown to over 3,000, each with unique characteristics, and they fall into several categories. The young pulsars, recently formed from supernova explosions, which tend to have slower spin rates and stronger magnetic fields. And as they age, they gradually slow down as their rotational energy is radiated away. And then there are the millisecond pulsars, spinning hundreds of times per second, which are thought to be old neutron stars that have been spun up by accreting matter from a companion star in a process called recycling. And there are magnetars, neutron stars with magnetic fields 1,000 times stronger even than typical pulsars, which occasionally produce intense bursts of X-rays and gamma rays. How many more varieties exist that we haven't yet discovered or categorized? The potential applications of pulsars extend into practical realms it would have seemed like science fiction to Jocelyn Bell and her colleagues. Astronomers have proposed using an array of precisely timed millisecond pulsars as a galaxy-scale detector for low-frequency gravitational waves, waves too long to detect with ground-based instruments like LIGO. And this pulsar timing array would work by detecting the tiny timing variations that gravitational waves passing through our galaxy. would induce in the arrival times of pulsar signals, and such waves might be produced by supermassive black hole binaries, or by exotic processes in the early universe. And the first evidence for such waves was announced in 2023. How do we turn natural phenomena into scientific instruments operating on astronomical scales? The question of what happens inside a neutron star at the boundary between neutron matter and hypothetical quark matter represents one of the outstanding mysteries in physics, because the pressures in the core may exceed what neutrons can sustain. And if quarks become deconfined, no longer bound into neutrons, but existing freely, the properties of the star would change in potentially observable ways. And some theories suggest that the transition might not be gradual, but sudden, a phase transition like water freezing into ice. And if such transitions occur, they might trigger starquakes, sudden shifts in the neutron star structure that would cause abrupt changes in its rotation rate. And such glitches have been observed in young pulsars, providing tantalizing but inconclusive hints about the exotic physics operating in their interiors. What exotic states of matter might exist in these natural laboratories? States we have barely begun to theorize about. The discovery of the first binary pulsar system where both objects are pulsars, the double pulsar system, PSRJ 0737339, has provided unprecedented opportunities to test general relativity, because we can observe how one pulsar signal is affected by the space-time curvature created by its companion, and the system is gradually losing energy to gravitational radiation, causing the orbit to shrink, and eventually, in about 85 million years, these two neutron stars will merge in a catastrophic collision that will produce gravitational waves detectable across the universe. And such neutron star mergers are now known to be the source of short gamma-ray bursts, and the primary production site for heavy elements like gold and platinum. How does understanding these extreme binaries change our understanding of where the elements of our world originated? The relationship between pulsars and fast radio bursts, or FRBs, has become a topic of intense investigation, because FRBs are millisecond duration bursts of radio waves coming from distant galaxies, and their origin was mysterious until 2020, when a burst was detected coming from a known magnetar in our own galaxy. And this provided the first definitive link between at least some FRBs and magnetars. And it suggests that the extreme magnetic fields of these objects can produce brief, intense radio emissions through mechanisms we are still working to understand. How many cosmic mysteries are connected in ways we haven't yet recognized, waiting for the key observation to link them? The exotic process of pulsar glitches illuminates the weird physics of neutron star interiors, because these sudden speed-ups in rotation occur when the rigid crust and the superfluid interior briefly fall out of synchronization, and then catastrophically recombine, and superfluidity, a state where matter flows without friction, is predicted to exist in the neutron star interior, because the neutrons can form Cooper pairs, analogous to those in superconductors. And when the crust slows due to magnetic braking, but the superfluid interior maintains its rotation, stress builds up until the crust suddenly cracks, and the interior transfers angular momentum outward, causing the pulsar to spin slightly faster before resuming its gradual slowdown. How do we study superfluidity and crustal fracture in an object we can never visit or sample directly? The use of pulsars for spacecraft navigation has moved from theoretical proposal to practical testing, because pulsar signals are so regular and come from known positions that they could serve as navigation beacons for deep space missions, providing a sort of cosmic GPS that doesn't depend on communication with Earth. And NASA's nicer instrument on the International Space Station has demonstrated this concept using X-ray pulsar timing to determine the station's position to within a few kilometers. And future missions to the outer solar system or beyond could use pulsar navigation to maintain accurate positioning when communication delays with Earth become prohibitively long. How does the universe provide infrastructure we can use for exploration and discovery? The connection between pulsars and the detection of gravitational waves represents one of the most profound synergies in modern astronomy, because pulsars serve first as evidence that gravitational waves exist through the orbital decay measurements, and then as potential detectors for low-frequency gravitational waves through pulsar timing arrays, and now with direct gravitational wave detection from LIGO and other instruments. We know that neutron star mergers produce both gravitational waves and electromagnetic signals, and by combining observations across these different channels, we can learn far more than from any single type of observation. What does multi-messenger astronomy reveal that single-channel observation cannot? The distribution of pulsars throughout our galaxy tells us about the history of star formation and death, because pulsars are born in supernovae and young pulsars cluster in regions where massive stars recently formed, and as they age, their beams weaken and they become harder to detect. And by mapping where pulsars of different ages are located and how they're moving through the galaxy, we can reconstruct the history of stellar death in our cosmic neighborhood over millions of years, and we can identify where new supernovae are likely to occur in the near future. How do we read cosmic history in the distribution of objects we observe today? The extreme conditions near pulsars make them sources of the highest energy particles in the galaxy, because the combination of rapid rotation and intense magnetic fields creates powerful electric fields that can accelerate particles to energies far exceeding what our largest particle accelerators can achieve. And these accelerated particles produce radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, and they may contribute to the cosmic rays that constantly bombard Earth from space. And understanding the particle acceleration mechanisms around pulsars helps us understand high-energy processes throughout the universe. What can we learn from nature's particle accelerators that we cannot learn from our own? The observation of pulsars in globular clusters, ancient, dense collections of stars orbiting our galaxy, has revealed some of the most rapidly spinning pulsars known. Millisecond pulsars that have been spun up through mass transfer from companion stars, and the dense environment of globular clusters facilitates close stellar encounters and the formation of exotic binary systems. And some of these systems involve pulsars orbiting white dwarfs or even other neutron stars. And the study of these systems provides insights into stellar evolution in dense environments and the complex interactions possible between collapsed stars. What unusual stellar configurations exist in the crowded cores of ancient star clusters? The discovery of intermittent pulsars, which switch between detectable and undetectable states over weeks or months, has challenged our understanding of pulsar emission mechanisms, because standard models predicted that pulsars should gradually and steadily slow down and fade, not turn on and off in apparently random patterns. And various explanations have been proposed involving changes in the magnetosphere, switches between different emission modes, or obscuration by material around the pulsar. But no single model fully explains all observed behaviors. How do anomalous objects force us to question our standard models and recognize gaps in our understanding? The potential connection between pulsars and dark matter has been explored through various proposals, including the possibility that dark matter particles might accumulate inside neutron stars and affect their properties, or that dark matter annihilation in neutron star cores might provide an additional energy source. And while no definitive evidence for such effects has been found, neutron stars represent one of the few environments where dark matter interactions might produce observable consequences, and searches continue for signatures that might reveal the nature of the mysterious substance that makes up most of the universe as matter. How do extreme objects serve as probes for cosmic mysteries beyond their immediate properties? The phenomenon of pulsar wind nebulae reveals the ongoing influence pulsars have on their surroundings long after the initial supernova has faded, because the high-energy particles and electromagnetic radiation streaming from the pulsar create a bubble of relativistic plasma that inflates into the surrounding medium, and this creates beautiful structures visible in X-rays and visible light. like the Crab Nebula surrounding its central pulsar, and studying these nebulae reveals how energy from rotating neutron stars is transferred to the interstellar medium, and how this process affects the chemical and energetic evolution of galaxies. How do stellar remnants continue to shape their environments across millennia? The timing precision of millisecond pulsars has enabled tests of fundamental physics beyond general relativity, including searches for variations in fundamental constants, tests of alternative gravity theories, and searches for ultra-low frequency gravitational waves that might be relics from the early universe. And the decades-long datasets now available for some pulsars provide baselines that can detect variations or anomalies that would be impossible to observe over shorter timescales. How does patience and observation, building datasets over decades, enable science impossible to achieve quickly? The role of pulsars in understanding supernova mechanisms connects these objects to their violent births, because the properties of the neutron star, its mass, spin, magnetic field strength, depend on the details of the supernova explosion. And by studying pulsar populations and correlating their properties with the remnants of their birth supernova, astronomers can constrain models of how massive stars explode. And recent observations suggesting that some neutron stars have masses exceeding 2 solar masses have challenged models of supernova energetics and the equation of state of nuclear matter. What do the children of stellar explosions tell us about the deaths that created them? The search for continuous gravitational waves from individual pulsars represents another frontier in gravitational wave astronomy, because if a neutron star has even a tiny asymmetry, a mountain on its surface just millimeters high, the rapid rotation will create a continuous gravitational wave signal, and detecting such signals would allow precise measurements of neutron star properties and test our understanding of how strong the neutron star crust can be before it breaks under the centrifugal stress of rapid rotation. What do we learn when we search for signals at the very edge of detectability? The evolution of isolated pulsars follows a predictable path from young, energetic objects gradually slowing and fading into invisibility. But this journey takes millions of years, and we observe pulsars at different stages of this evolution. From the Crab pulsar, only about 1,000 years old, and still surrounded by the remnant of its birth supernova, to millisecond pulsars billions of years old that have been recycled through mass transfer. And this range allows us to study not just a static phenomenon, but a complete life cycle. How does observing objects at different life stages allow us to understand processes operating across timescales far longer than human civilization? The question of whether all neutron stars are pulsars, or whether only certain conditions produce the beaming geometry that makes them visible to us, has implications for estimating the total neutron star population in our galaxy, because we can only see pulsars when their beam sweeps across Earth. And if the beams are narrow, we might miss most neutron stars. And estimates suggest that for every pulsar we observe, there might be 10 or more neutron stars whose beams don't point our way. And some neutron stars might have magnetic fields too weak to produce observable pulses at all. How do we account for selection bias when we can only observe objects that happen to be oriented favorably toward us? The exotic possibility of strange quark stars, objects even denser than neutron stars, where the quarks throughout the star exist freely, rather than being confined into neutrons, remains speculative but tantalizing. Because if the strange quark state is the true lowest energy state of matter at extreme densities, then neutron stars might actually be metastable and could undergo a phase transition to strange stars. And such objects would have different properties, different maximum masses, different cooling rates, different radii. And some observed objects that don't quite fit neutron star models might potentially be strange stars. Though no definitive evidence exists, what undiscovered forms of matter might exist in conditions we cannot replicate or easily observe? The contribution of pulsars to our understanding of stellar evolution extends beyond their own life cycle. Because the supernova explosions that create neutron stars disperse heavy elements into the interstellar medium, enriching the gas from which new stars form, and the energetic outflows from young pulsars and pulsar wind nebulae inject energy that can trigger or suppress new star formation. And thus, these stellar corpses play an active role in galactic ecology, influencing the next generation of stars. Even as they slowly fade, how do endings and beginnings intertwine in the cosmic cycle of stellar birth and death? The observational techniques for studying pulsars continue to evolve, with new radio telescope arrays providing unprecedented sensitivity and time resolution, and space-based X-ray and gamma-ray observatories revealing high-energy emission that complements radio observations. And future instruments, like the Square Kilometer Array, will detect pulsars too faint for current telescopes, and will enable even more precise timing measurements. And each improvement in observational capability reveals new phenomena and raises new questions. How does advancing technology continually refresh our perspective on even well-studied objects? The educational and cultural impact of pulsars extends beyond professional astronomy, because these objects capture imagination in ways that more abstract phenomena sometimes don't. And the story of Jocelyn Bell's discovery and the initial speculation about alien signals provides a compelling narrative about scientific process. And the extreme physics of neutron stars challenges intuition and demonstrates the universe's capacity to exceed human experience. And the precision of pulsar timing demonstrates how patience and careful measurement can reveal profound truths. How do particular astronomical objects become ambassadors for science more broadly? The ongoing mysteries surrounding pulsars ensure they will remain subjects of intense study for decades to come. Because despite 50-plus years of observation and theory, fundamental questions remain. What exactly is the emission mechanism? What is the internal structure? How strong can magnetic fields become? What happens at the boundary between neutron matter and quark matter? Can we detect continuous gravitational waves from individual pulsars? Are there exotic variants we haven't yet discovered? And what can pulsar observations reveal about dark matter, gravitational physics, and cosmic history? How comfortable are we with the fact that some of the longest studied objects in modern astronomy still harbor deep mysteries? The precision and reliability of pulsars creates a curious irony, because these objects born in violent explosions and existing in the most extreme conditions become through their very extremity sources of stable reference signals that help us explore other astronomical phenomena. And the lighthouse metaphor captures something essential. These beacons weren't built for us, but we can nevertheless use them to navigate and explore. And they remind us that the universe, however indifferent to human purposes, nevertheless provides tools for understanding itself. What does it mean that cosmic violence creates cosmic precision? The legacy of pulsar research demonstrates how unexpected discoveries can revolutionize multiple fields, because no one set out to find pulsars, were discovered accidentally while studying something else entirely, and their existence forced physicists to take seriously the theory of neutron stars, which had been speculative, and they provided laboratories for testing general relativity in strong field regimes. And they became tools for detecting exoplanets and gravitational waves. And they continue to surprise us with new phenomena decades after their discovery. How often do the most important discoveries come not from finding what we sought, but from recognizing the significance of what we stumbled upon? And so the lighthouses shine on, scattered through our galaxy and beyond, corpses of ancient stars spinning in the darkness, broadcasting their precise rhythms to anyone with instruments to receive them. Each pulse a reminder of stellar death and extreme physics. Each timing variation a clue to invisible phenomena. Each newly discovered pulsar a fresh opportunity to probe the limits of what matter can endure and what nature can create. And as our telescopes grow more sensitive and our timing more precise, we continue to hear the voices of these celestial lighthouses, steady and mathematical, neither conscious nor intentional, but nevertheless informative, guides not to safe harbor, but to deeper understanding of the cosmos that created them and us. Before you drift into sleep, remember mystery is never truly lost, only waiting to be found. If you enjoyed this journey through the cosmic lighthouses, subscribe for more relaxing explorations of ancient mysteries and modern wonders, and let your curiosity guide you deeper into the universe's secrets.